Good day, guys. Hi to the future mechanical engineers, especially to BSME 1B Ladderized Engineering Program. Today, I'm going to discuss one of the topics under fluid mechanics, which is the concept of buoyancy. Now, in elementary physics, even in high school physics, we were already introduced to the concept of buoyancy. As we all know, object that has density lower than the density of water will float on top of water. Say for example, oil, wood, styrofoam, ball with air inside. So these are just some examples of the object that will float on top of the water. However, in engineering studies, understanding about buoyancy principle is not limited to determining whether an object will float on top of a fluid or not. We we really have to understand the buoyancy in order to design a certain mechanical system, or to use it in practical situations. Say for example, we are going to design a boat that could carry, say, ten persons. In that case, we have to determine the volume that should be displaced by the boat in order to carry 10 persons. It means that volume should be displaced by the boat. So we can use that in the design of the boat. And that is just only some examples. Now to continue our discussion with buoyancy, so let us just have a review about the concept of buoyancy. As we all know, buoyancy was introduced by Archimedes, or this is also known as the Archimedes Principle. He discovered this during the time that he was compelled to determine the amount of gold that is in the king's crown. He was really challenged, and he realized that he can use the concept of buoyancy. So he went out and shouted the word Eureka, which means I found it. Buoyancy is just simply the tendency of an object to float in the fluid. It is an upward force equal to the weight of the displaced fluid. As we all know, when you put an object in the fluid, the object will displace the fluid, since there are no two objects that they can occupy the same space at the same time. So the object has to displace the fluid in order to occupy the space. The formula that we can use in determining the buoyant force exerted by the fluid is buoyant force is equal to the specific weight of the fluid times the volume of the fluid displaced. We all know that the specific weight of the fluid is actually equal to the ratio between the weight of the fluid all over the volume occupied by the fluid, as discussed in the previous discussion regarding the properties of the fluid. So, naturally, an object will float in a fluid if the specific gravity of the object is less than or equal to the specific gravity of the fluid, such as the examples that we have mentioned a while ago. To continue our discussion with the concept of buoyancy principle, let me give you another trivia question for this video. And the trivia question is, what are the forces that act on our airplane? Most of us has already seen an airplane is in the sky. So what do you think are the reasons why it can maintain that elevation and that speed, and it can travel along that distances at a certain direction? Now to continue our discussion with buoyancy, let us try to analyze these three containers that contains fluid. So you have container 1, 2, and 3, in which we're going to discuss three sample cases in dealing with buoyancy. For case number 1, say we have specific gravity of the fluid is equals to the specific gravity of the object. And we put an object in the fluid, so the object will displace the fluid. However, since the specific gravity of the fluid is equal to the specific gravity of the object, then they are in neutral. It means that their surfaces will be on the same level. So it only means that the volume displaced by the volume of the fluid displaced is equals to the volume of the object. And we can also conclude that the buoyant force is simply equal to the weight of the object. Now for case number 2, assuming we have a specific gravity of the fluid is greater than the specific gravity of the object. In this case, we can simply conclude that an object will float on top of the fluid. So it means that part of the volume of the object will be submerged in the fluid while some of the parts will be exposed on top of the fluid. In this case, the volume of the fluid displaced is less than the volume of the object. However, since the specific weight of the fluid is great enough to sustain the buoyant force to lift the object, so it means that the buoyant force is equal to the weight of the object. Now for case number 3, assuming we have a specific gravity of the fluid is less than the specific gravity of the object, say for example, stones, metal. When you put stone or metal, those kinds of objects will completely be submerged or sink in water. So it means that the volume of the fluid displaced is equal to the volume of the object. However, the buoyant force is insufficient to sustain the weight of the object. So these are some of the possible cases when you put an object in the fluid. And now, let's just try to discuss sample problems. Say for example, we have a block of square wood, 5 cm on each sides and length of 15 cm is placed in water. The specific gravity of wood is 0.52. So we have to determine the following. First, the weight of the block. Second, volume of the water displaced. Third, part of the block on top of the water surface. And this is the illustration. So you have a block of square wood with a height of 15 cm will be placed in water. Now for the given, we have height of the block 15 centimeters, convert to meter, you have 0.15 meter. Side of the block is equals to 5 centimeter, convert to meter, you have 0.05 meter. Specific gravity of the block is equals to 0.52. And since we use water, or the fluid is water, we can use the specific weight of the fluid at the standard or the water at standard temperature and pressure, which is equals to 9,810 Newton per cubic meter. For the solution, we have the specific weight of the block is equals to the specific gravity of the block times the specific weight of the water. So substituting the value, specific gravity is 0.52 and the specific weight of water is 9,810 Newton per cubic meter. We can simply say that the specific weight of the block is 5,101.2 Newton per cubic meter. Now for the volume of the block, that is equals to the area of the sides times the height, where the area of the sides is equals to s squared since we have a square block, so s squared times h. Substituting the value, so the volume of the block is equals to 3.75 times 10 raised to the negative 4 cubic meter. Now for the weight of the block, take note that the weight of the block is also equal to the specific weight of the block times the volume of the block. And then substituting the value, so the weight of the block is equals to 1.913 Newton. For letter B, we're going to determine the volume of the water displaced. So by free body diagram, there are two main forces that acts on the object. First, we have a downward force due to the weight of the block, and we have an upward force due to the buoyant force. So it only means by summation of forces along y-axis, it only means that the weight of the block is simply equal to the buoyant force, while the buoyant force is equal to the specific weight of the water times the volume of the water displaced. So the volume of the water displaced is simply equal to the weight of the block, which is also equal to the buoyant force all over the specific weight of the water. And substituting the value, we can simply say that the volume displaced, or the volume of the displaced water, is equals to 1.95 times 10 raised to the negative 4 cubic meter. It shows that the volume displaced is less than the volume of the object. So it means that the object is partially submerged in water. To determine the part of the black on top of the water surface, we can say that the volume of the fluid displaced is equals to the volume of the black submerged. Well, the volume of the black submerged is equals to the area of the black times height of the black submerged. So therefore, the height of the black submerged is equals to the volume of the black submerged all over area of the black. Substituting the value, the height of the black submerged in water is equals to 0.078 meter, or simply that is equals to 7.8 centimeters. So therefore, the height of the black on top of the water surface is equals to the total height of the black minus the height that is submerged. Substituting the value, we can say that the height of the black on top of the water surface is equals to 7.2 centimeters. Therefore, the volume of the black on top of the water surface is equals to area of the black times height of the black on top of the water surface. Substituting the value, we can say that the volume of the black on top of the water surface is equals to 1.8 times 10 raised to the negative 4 cubic meter. Assuming that x sub f represents the portion of the black or part of the black on top of the water surface that is equals to the volume of the black on top of the water surface all over the total volume of the black. We all know that the volume of the black on top of the water surface is equals to the height on top of the water surface times the area of the black all over the total volume of the black, which is equals to the area of the black times the total height. Cancelling out the area of the black, therefore x sub f is equals to hf all over h. And then substituting the value, we can say that x sub f is equals to 0.48, or it means that 48% of the total volume is on top of the water surface, while 52% of the volume of the black is submerged in water. Say for number 2, we're going to use same given as problem number 1, except that the fluid is alcohol instead of water. So the specific gravity of alcohol is equals to 0.72. Similarly, we're going to determine the volume of the alcohol displaced and the part of the black on top of the alcohol surface. So we have the given. Again, the height of the block is 0.15 meters. Side of the block is 0.05 meter. Specific gravity of the block is 0.52, while the specific gravity of the fluid, in this case, is alcohol, is 0.72. And we are going to use the specific weight of the water, which is equals to 9,810 Newton per cubic meter. For the volume of the alcohol displaced, again, identifying the two major forces in the system, we have weight of the black is equals to the buoyant force. Now, the buoyant force is equals to the specific weight of the fluid times the volume displaced, while the volume displaced is equals to the buoyant force all over the specific weight of the fluid. And the specific weight of the fluid is simply equal to the specific gravity of the fluid times the specific weight of the water. Therefore, substituting the value, the volume of the alcohol displaced is equals to 2.708 times 10 raised to the negative 4 cubic meter. As you can see, the volume of the alcohol displaced is larger than the volume of the water displaced, simply because the specific gravity of water, which is equals to 1, is greater than the specific gravity of alcohol, which is equals to 0.72. Now, for the part of the black on top of alcohol surface, using the same formula, volume of the alcohol displaced is equals to the volume of the black submerged. So the height of the black submerged is equals to the volume of the black submerged all over area of the black. And then substituting the value, we found out that the height of the black submerged is equals to 0.1083 meter, or that is 10.83 centimeters. So the height of the black on top of the alcohol surface is equals to the total height of the black minus height of the black on top submerged in alcohol, and that is equals to 4.17 centimeters. So the volume of the black on top of the alcohol surface is equals to 1.0425 times 10 raised to the negative 4 cubic meter. It shows that this value is smaller than the volume of the black that is on top of the water surface. And the percentage of the black on top of the alcohol surface is equals to 27.8% compared to the percentage of the black on top of the water surface. This one is smaller because, again, as we all know, the specific gravity of the alcohol is less than the specific gravity of water. So it means that a greater portion of the wood should be submerged in the alcohol, or the wood has to displace greater amount of alcohol in order to provide a sufficient amount of buoyant force to sustain the weight. Now, to sum it up, on problem number 1, we have water, and the height of the block on top of the water surface is 7.2 centimeters, while the volume of the water displaced is 1.95 times 10 raised to the negative 4. But for problem number 2, we have the fluid is alcohol with specific gravity of 0.72, and we found out that the volume displaced is 2.708 times 10 raised to the negative 4 cubic meter. It means that this one is higher than the volume of the water displaced, while the height of the block on top of the alcohol surface is only 4.17 centimeters. Now, you might now get your calculator. What if you are given a fluid which is oil with a specific gravity of 0.88? What portion of the block will be on top of the oil surface? Can you do the calculations? Are you done? So what is the height of the block on top of the oil surface? And the answer is 6.14 centimeters. And the volume of the oil displaced is 2.216 times 10 raised to the negative 4 cubic meter. As you can see, the higher the specific weight of the fluid, the smaller the volume displaced, while the height of the block on top of the surface of the fluid is higher when the specific gravity of the fluid is higher. Now let us try another problem number 3. We have a block of wood, square wood, 7 cm in each sides is placed in fluid 1 with a specific gravity 1.2 and then placed in fluid 2 with a specific gravity 2 of 0.82. The difference between the height submerged in each fluid is 5.02 centimeters. The specific gravity of wood is 0.52. Determine the following: A. Height and volume of the block. B. Height submerged in fluid 1. C. Height submerged in fluid 2. To illustrate, we have a block of wood and we have two fluids. We have fluid 1 with a specific gravity of 1.2 and we have fluid 2 with a specific gravity of 0.82. We can expect that the wood will displace greater amount of fluid 2 than fluid 1 since the specific gravity of fluid 2 is less than the specific gravity of fluid 1. Now we have this given. The sides of the block is 7 cm. Specific gravity of fluid 1 is 1.2. Specific gravity of fluid 2 is 0.82. So it means that the specific gravity of fluid 1 is greater than the specific gravity of fluid 2. So the height submerged in fluid 1 is less than the height submerged in fluid 2 as shown in the figure. So it only means that the difference between the height submerged in fluid 2 minus the height submerged in fluid 1 is equals to 5.02 cm, while the specific gravity of the block is equal to 0.52. To solve the problem, first, we're going to determine the height and the volume of the block. Now, we all know that the weight of the block is simply equal to the specific weight of the block times the volume of the block, while the specific weight of the block is simply equal to the specific gravity of the block times the specific weight of the water. Now, for the volume of the block, that is just simply equal to the side squared times the height. Now, for the buoyant force 1 is equals to weight of the block. We all know that the buoyant force 1 is simply equal to the specific gravity of fluid 1 times the specific weight of the water times the volume of fluid 1 displaced. So the volume of the fluid 1 displaced is equals to the area of the block times the height of the block that is submerged at fluid 1, or that is equals to S squared times HS1. So therefore, the buoyant force on fluid 1 is equals to the specific gravity of 1 times specific weight of water times the area of the block times the height of the block submerged in fluid 1. Equating the two formula, so we have the weight of the block is equals to the buoyant force 1. Canceling out the terms specific weight on both sides of the equation and S squared on both sides of the equation, we have specific height of the block submerged in fluid 1 is simply equal to the specific gravity of the block times the total height of the block all over the specific gravity of fluid 1. So similarly, we can simply say that the height of the block submerged in fluid 2 is equals to the specific gravity of the block times the total height of the block all over the specific gravity of fluid 2. And then substituting the value, we have height of the block submerged in fluid 2 minus height of the block submerged in fluid 1 is equals to the specific gravity of the block times height of the block all over specific gravity of fluid 2 minus specific gravity of the block times total height of the block all over specific gravity 1. Now, as you can see, both terms have a specific gravity of the block times the height. So, factoring out the specific gravity of the block times the height, we'll come up with HS2 minus HS1 is equals to specific gravity of the block times the height multiplied by the quantity of 1 minus the specific gravity of fluid 2 minus the specific gravity of fluid 1. So substituting the value, we'll come up with H is equals to 25 centimeters, or that is 0.25 meter. So the volume of the block therefore is equals to 1.225 times 10 raised to the negative 3 cubic meter. For letter B, we're going to determine the height of the block submerged in fluid 1. So the height of the block submerged in fluid 1 is equals to the specific gravity of the block times the total height of the block all over the specific gravity of fluid 1. Substituting the value, HS1 is equals to 10.83 centimeter. While for the height submerged in fluid 2, using the same formula, we found out that the height of the block submerged in fluid 2 is equals to 15.85 centimeters. So as you can see, the height of the block submerged in fluid 2 is higher than the height of the block submerged in fluid 1, simply because the block has to displace greater amount of fluid 2 to sustain or to carry its weight. Say for example number 4. A block of square wood 5 cm in each sides and has a length of 15 cm. Now the specific gravity of wood is equals to 0.52. Determine the additional weight to be placed in one end of the block to completely submerge the block in water. So we have, let's say that blue object on top of the block has a weight W sub O. And then when you put that weight on top of the block, it should completely submerge the block in water. So we have the following given. The height of the block is 15 centimeters. The side is 5 centimeter. Still, the specific gravity of the block is 0.52. Now, and the specific weight of the water is 9,810 Newton per cubic meter. For the solution, now we have two forces acting downward, which are the weight of the block and the weight of the object, which should be carried out by the buoyant force, which is upward. So by summation of forces along y-axis, it only means that the weight of the block plus the weight of the object is equals to the buoyant force, while the weight of the object is equals to the buoyant force minus the weight of the block. And the buoyant force is equals to the specific weight of the water times the volume of the water displaced. And the weight of the block is equals to the specific weight of the block times the volume of the block. Now in this case, since the block will be completely submerged in water, it means that the volume of the block is equals to the volume of the water displaced, and that is equal to 3.75 times 10 raised to the negative 4 cubic meter. Now therefore, the weight of the object is equals to the specific weight of the water times the volume of the water displaced minus the specific weight of the block times the volume of the water displaced. Factoring out the volume displaced, you have specific weight of the water minus specific weight of the water times specific gravity of the block. We all know that this term is actually the specific weight of the block. So therefore, factoring out the specific weight of water, we can simply say that the weight of the object is equals to the volume of the water displaced times the specific weight of the water times 1 minus the specific gravity of the block. Substituting the value, we can simply say that the weight of the object needed in order to completely submerge the wood, a block of wood, in water is equals to 1.7658 Newton. For the next problem, we have example number 5, a concrete block, a specific gravity of 2.4 with a mass of 2 kg is placed in water. What tension is needed to hold the concrete fully underwater? So this time, we have an object that has a specific gravity greater than the specific gravity of water. So we can expect that the object will completely sink in water. And the question is, what is the needed tension in order to hold the concrete fully underwater? So it means that it should float in water while its volume is completely submerged in the fluid. So we have the following given. Specific gravity of the concrete is 2.4. Mass of the concrete, 2 kg. Specific weight of the water is 9,810 Newton per cubic meter. So the solution, we have the weight of the concrete is equals to the buoyant force plus the tension. As we all know from the previous diagram, that the weight of the concrete is acting downward while both the buoyant force and the tensile force or the tension is acting upward. For the weight of the concrete, that is equals to the mass of the concrete times the acceleration due to gravity. And substituting the given mass and the acceleration due to gravity, so it will give us a weight of the concrete equals to 19.614 Newton. For the buoyant force, it is equals to the specific weight of the water times the volume submerged, while the volume of the concrete submerged is equals to the volume of the concrete since the object will be completely submerged in the fluid. So therefore, the volume of the concrete is equals to the weight all over the specific weight of the concrete. And the specific weight of the concrete is equals to the specific gravity of the concrete times the specific weight of the water. So substituting the values, so the volume of the concrete is equals to 8.331 times 10 raised to the negative 4 cubic meter. And solving for the buoyant force, so the buoyant force is equals to 8.173 Newton. So therefore, the tension is just simply the difference between the weight of the concrete minus the buoyant force. And it will give us a value of 11.441 Newton. So it means that this is the amount of force needed to raise the object or the concrete block to float in the water with all of its volume submerged in the fluid. What if instead of applying a tension on the block, we're going to use a buoy in the form of styrofoam with a specific gravity of 0.33 to hold the concrete block completely on top of the water surface. So you have the following given. Specific gravity of the concrete is equals to 2.4. The mass of the concrete is 2 kilograms. The specific gravity of the styrofoam is 0.33. and the specific weight of the water is 9,810 Newton per cubic meter. So we're going to determine the amount of styrofoam needed to hold the concrete completely on top of the water. So we have the weight of the concrete plus the weight of the styrofoam is equals to the buoyant force. While the weight of the concrete is simply equal to the mass of the concrete times the acceleration due to gravity. Also, the weight of the styrofoam is equals to the specific weight of the styrofoam times the volume of the styrofoam, or that is equals to the specific gravity of the styrofoam times the specific weight of the water times the volume of the styrofoam. Now, the buoyant force is equals to the specific weight of the water times the volume of the object submerged. Now, this case, the volume of the object submerged is actually equal to the volume of the styrofoam, since the concrete rock will be completely on top of the water surface. So, using this equation, we can simply say that the weight of the concrete is equals to the buoyant force minus the weight of the styrofoam. Now, this one is the buoyant force minus this one is the weight of the styrofoam. And then factoring out the specific weight of the water times the volume of the styrofoam, we'll come up with weight of the concrete is equals to the specific weight of the water times the volume of the styrofoam times 1 minus the specific gravity of the styrofoam. Now, solving for the volume of the styrofoam, that is equals to the weight of the concrete, this one, divided by specific weight of the water, which is this one, times 1 minus the specific gravity of the styrofoam. And then substituting the value, it will give us a value of the styrofoam is 2.984 times 10 raised to the negative 3 cubic meters. So that should be the volume of the styrofoam needed in order to lift the concrete 2 kilograms concrete block. And the mass or the weight of that styrofoam is equals to 9.66 Newton. So that styrofoam should have a volume of, or this styrofoam should have a volume of 2.984 times 10 raised to the negative 3, and it should have a weight of 9.66 Newton. And for our next problem, we have example number 7. A spherical ball with radius of 8 cm is filled with air. The ball is then placed in water. What tension is needed to hold the ball beneath the water surface? That is, neglecting the weight of the ball material. So we have the following given. The radius of the ball is equals to 8 centimeters, or that is 0.08 meter, while the specific weight of the water is 9,810 Newton per cubic meter. The density of air is equals to 1.2 kilogram per cubic meter. As you can see, if we're going to neglect the weight of the ball material, what we're going to consider is the weight of the air inside the ball. Now, since the density of air is very small in comparison with the density of water, which is 1,000 kilogram per cubic meter, so it is quite impossible for the ball to sink beneath the water surface, not unless an external force is applied. And that's what we're going to solve. That is represented by the arrow going down. Now for the solution, we have weight of the ball plus the tension is equals to the buoyant force as shown on the previous figure. However, since we're going to neglect the weight of the ball material, so the weight of the ball will simply represents the weight of the air inside the ball. So the weight of the ball is equals to the specific weight of the air times the volume of the air, while the specific weight of the air is equals to the density of the air times the acceleration due to gravity. Now, solving for the volume of the ball, since the ball is spherical, the volume is 4 over 3 pi r cubed. And substituting the given value, so the volume of the ball is equals to 2.145 times 10 raised to the negative 3 cubic meter. And then substituting the given values such as the density of the air times the acceleration due to gravity times the volume of the ball, so the weight of the ball is equals to 0.025 Newton. Solving for the buoyant force is equals to the specific weight of the water times the volume of the ball. Since the volume of the ball is equals to the volume of the water displaced, considering that the whole volume of the ball will be placed beneath or will be submerged beneath the water surface. So the buoyant force is equals to 21.04 Newton. Now to solve for the tension, so using the equation above, tension is therefore equal to the buoyant force minus the weight of the ball. So the tension is equals to 21.04 Newton, which is the buoyant force, minus 0.025 Newton, which is the weight of the ball. And the answer is 21.017 Newtons. It only means that you have to apply a downward force of 21.017 Newton in order for the ball to be placed beneath the water surface. Maybe all of us has experienced carrying an object in air. And then when we carry the same object in water or in fluid, it seems like the object becomes lighter. That is simply because there is a weight loss in water. An example of that is a lifesaver such as air balloon or an empty container. We all know that an empty container will not float in air. However, when you put that in water, it can be used for flotation purposes or as a buoy. Now, that concept can also be used in order to determine the specific gravity of an object, especially if the specific gravity of an object is greater than the specific gravity of the fluid, such as water. Now, what we're going to do is, in order to determine the specific gravity of an object, the first thing that we have to do is to determine its weight in air, which is the normal weight, and determine its weight in water using a spring scale. Now, the formula for the specific gravity of the object is just simply equal to the mass in air all over the mass in air minus mass in water, or that is also equal to the weight in air all over the weight in air minus the weight in water. Now, the weight in air minus weight in water is known as the weight loss in water. Another thing is we can also use these concepts in determining the specific gravity of an unknown liquid. All we have to do is, again, to get an object and then determine its mass in air using spring scale, and then put the same object in water and determine its mass in water, and then put the same object in another fluid or in an unknown fluid and determine its mass in that fluid. Now, to determine the specific gravity of an unknown fluid or an unknown liquid, that is simply equal to the weight in air minus weight in an unknown fluid all over the weight in air minus weight in water. Now, take note that the numerator is actually the weight loss of the object in an unknown fluid, while the denominator is again the weight loss of the object in water. Now, say we have this example. We have a metal weighs 20 grams in air and 8 grams in water. When placed in an unfluid, it weighs 12 grams. We're going to determine the specific gravity of the object and the specific gravity of the unknown fluid. Now we have the following given. Its weight in air is equal to 20 grams, while the weight in water is equal to 8 grams. Weight in the unknown liquid is 12 grams. Now for the solution, we have specific gravity of the object is equals to the weight in air all over the weight loss in water, which is equals to the weight in air minus weight in water. Substituting the given values, we found out that the specific gravity of the object is equals to 1.67. Now for the specific gravity of the unknown fluid, we can use the formula weight loss in the unknown fluid all over the weight loss in water. And substituting the value, we have the weight in air minus the weight in unknown fluid all over the weight in air minus the weight in water. And the value of the specific gravity of the unknown fluid is equals to 0.67. So next time, when you encounter this kind of situation where you're going to determine the specific gravity of an object, one way is to use the concept of buoyancy. Now, before we end this video, let us try to answer the trivia question that I have given to you a while ago. And my trivia question is, what are the forces that acts on the airplane? Now, we all know that the density of the airplane is higher than the density of air. So how does the airplane flies above the ground, considering that its density is higher than the density of the air? Is it mainly because of the buoyancy, or are there any other forces that acts on the airplane? And to answer that question, actually there are four major forces that acts on the airplane as it flies above the ground. First is the thrust force. Thrust force is simply the force created by the propeller or rocket that allows the plane to move into the desired direction. It pushes the airplane towards its desired direction. While there is also a force that opposes the flight of the airplane, and that force is known as the drag force. Drag force is simply the force due to the air resistance opposing the motion. And this force is very useful, particularly when braking the airplane to stop. Another force that acts on the airplane as it flies above the ground is the lift force. The lift force is the force that is created by the wings of the plane and hold it in the air. Actually, the lift force is equals to the mass of the air displaced per second multiplied by the velocity of the airplane. And lastly, we all know that the airplane is acted upon by the acceleration due to gravity, and that is due to its weight. As we all know, the direction of the weight is towards the center of the earth or towards the ground. So it means that this opposes the lift force. And those are the four major forces that acts on the airplane as it flies above the ground. And as you can see, the concept is beyond buoyancy. And that concept is more on aerodynamics. And that answered the trivia question. Thank you for watching the video. Hope to see you on my next video. God bless.